So last class session, we discussed mixtures, pure substances, elements, and compounds. So our first order of business is we're going to review these concepts with a problem-solving example. And I'm going to need your help in the chat to help facilitate this discussion. So the first question I have is, which mixture is homogeneous? Mixture A or mixture B? So which of these two mixtures appears homogeneous with consistent composition? I see a lot of A's. That's correct. Exactly right. Mixture A is homogeneous, has a consistent composition, and there's no clear phase boundary. Mixture B, we see a clear phase boundary, which is indicative of a heterogeneous solution. Now, I'd like you to look specifically at the structures found in each of these zoom in circles. I'd like you to know that different colors represent different elements. So my question to all of you is, when we look at, for example, octane, so octane is referring to this molecule, this species here. And looking at octane, would we classify it as an element or a compound? Do we see one element or multiple elements? So looking at octane, do we see one color or multiple colors in its structure? So looking at octane, we definitely see two or more elements. That's why we see two or more different colors in its structure. So then octane would clearly be a compound. Octane's formula would be C8H18. And as we can clearly tell, we clearly can see two or more different elements. So this would be a compound. Looking at carbon tetrachloride, CCl4, now we have the formula, so it's a little easier to parse. Is carbon tetrachloride an element or a compound? Do we see one element or do we see two or more elements chemically bonded? So carbon tetrachloride would definitely be a compound, as it has two or more different elements chemically bonded. Does that make sense to everyone? Elements have just one element in their formula, and they can have any number of atoms. Compounds have two or more different elements chemically bonded as part of their formula. Does that make sense to everyone? Any questions on that? Let's do the same thing for mixture B. So if we think about gasoline, so if we look at the formula for gasoline and we look really closely at, so if we look really closely at the species that make up this gasoline sample, just looking at one of these molecule pictures, do we see a single element or do we see two or more different elements chemically bonded? Two or more. So then what would we call this then? An element or a compound? Compound, exactly right. So gasoline contains molecular compounds. Likewise, and this one should be a freebie. Water, H2O, is it an element or a compound? Do we see just one element symbol or do we see two or more different element symbols? Water is a compound because we have hydrogen and oxygen, two or more different elements bonded together. Does that make sense to everyone so far? Any questions on this idea? it's important that you know how to identify elements and compounds because the way that we name elements and compounds is fundamentally different. Okay, so let's now talk about the next major idea with regards to classifying matter. So we're now going to discuss chemical and physical properties. So elements and compounds can react and convert to new compounds, or they can decompose to their component elements via chemical changes. Now, what is a chemical change? It's a process that changes the chemical composition of matter. And yes, and for the students who are in the process of adding, you can write these notes separately. I'll also be uploading these notes annotated to Canvas as well. So a chemical change is a process that changes the chemical composition of matter, and chemical changes are primarily, overwhelmingly, chemical reactions. Okay? So in a chemical reaction, our starting material or our reactants will break and make chemical bonds to form new pure substances that we call products. The products have a different chemical formula, a different arrangement of chemical bonds, and or a different number of atoms as part of their formula. Now, a critical feature of all chemical reactions is that atoms are conserved and mass is conserved. The total number of atoms of each element before and after a chemical reaction does not change. So, chemical changes, we change the chemical composition of matter. Chemical equations represent and describe chemical changes and chemical reactions by describing the conversion of reactants, our starting materials, to our products. So reactants are this chemical species that are reacting in our chemical reaction. Products are the chemical species produced in our reaction. Now, to give everyone an introduction to how we read chemical equations, there are a few things that you need to be familiar with. Well, the reactants are on the left, the products are on the right, and in the middle is what's known as the reaction arrow. This indicates the reactant and product sides of the chemical equation. Now, just like always, we also have our good old friends, the state symbols. So we have our state symbols. And the state symbols indicate the physical state of each substance. We'll learn more about the rules for assigning physical state, but for all of our elements, it's pretty familiar to us, the physical states of most elements. So you know oxygen, for example, is a diatomic gas from our last lecture. Now, in terms of our additional parts of this chemical equation, you may notice these numbers in front of each chemical formula. These are called reaction coefficients. And the reaction coefficient indicates the number of each molecule, atom, or compound that participates in your reaction. The reaction coefficient must be a whole number. There's no such thing as half a molecule, just like the idea of half an atom doesn't make any sense. We'll see more from these chemical equations later on in this course. I just want you to be familiar with, for now, the basic structure of a chemical equation and how to read these chemical equations. We won't be using these until later, but an introduction can help make it easier to recall these concepts later on in the class. Let's look now at some evidence of chemical changes. So chemical changes or reactions can be indicated by the formation of gas, formation of a solid precipitate, color changes, or the generation of heat or light. So here we see three examples of chemical changes where we are clearly generating gas, generating light or heat, or generating a solid. Remember, our baseline definition of a chemical change is that a chemical change changes the chemical formula or composition of matter. So for example, anytime you're generating a product with a different chemical formula than your reactants, you are likely undergoing a chemical change. So this would be an example of a chemical change, reaction of sodium and chlorine to yield sodium chloride, because as we can see, if we compare the formula for sodium and sodium chloride, is the formula the same or different? Does the formula look the same or different? Different. Exactly. Okay. So we understand this idea of chemical changes. Let's now talk about chemical properties. Whoops, one moment. So chemical properties are a property observed when a substance changes chemical composition or undergoes a chemical change. Chemical properties concern reactivity. So some questions to ask that relate to chemical properties. How does the species react? What occurs during a reaction? So here are some examples of some chemical properties. Sodium reacts with water. So this reacts is a very important keyword to know. Another example would be chlorine generates heat when reacting with aluminum. Again, we see the react keyword and this idea that it generates heat during the reaction is a chemical property. Another example would be noble gases are relatively inert, which means relatively non-reactive. So you may notice when we talk about chemical properties, what keyword do we see overwhelmingly? Let me rewrite this a little bit more clearly. What keyword do we see overwhelmingly? React, exactly. Chemical properties concern reactions. Okay, so we've seen chemical changes and chemical properties. Any questions on this? Any questions that I can address? If not, let's now talk about physical changes. Physical changes do not change the chemical composition of a substance. So there's no change in formula. Okay, this will be important. That's their key metric. There's no change in the chemical formula for a physical change. So here are some common physical changes. Phase changes. So when a sample of matter changes from one physical state to another with no change in formula. So if we think about phase changes, so common keywords for phase changes are evaporate, that's from liquid to gas, melts, that's going from solid to liquid, and then sublimes is going from solid to gas. And yes, for the students who are added this week, you'll have access to the notes in Canvas, and you'll be able to receive the copies of this note set. So don't worry about that. So these are some keywords that you want to be familiar with for phase changes: evaporates, melts, sublimes. These are all keywords that indicate the transition from one physical state to another. Now, physical changes and phase changes are physical changes because if we think about a phase change process, so for example, dry ice subliming, we're going from carbon dioxide solid to carbon dioxide gas. My question to all of you is, if we look at the formula before and after this physical change, does the formula change? Does the formula change? No. So we have the same formula. And as a result, there's no change in chemical composition. So this is a physical change. Phase changes, changes in physical state are physical changes. Does that make sense to everyone? No matter that the dry ice is subliming, carbon dioxide, which is dry ice, remains carbon dioxide. It has just changed physical state. The other common physical change that you need to be familiar with is mixing or dissolving two or more substances. So the key word is solubility, and dissolves, and mix. Okay, so when a substance dissolves, so looking at sugar, when sugar dissolves, we're going from the solid state to the aqueous state. But again, as we've seen time and time again, does the formula change when sugar dissolves? Does the formula change? No, we have the same formula. So our chemical composition is the same, and as a result, this is a physical change. So when a substance dissolves, the chemical formula does not change, only the physical state. So phase changes and solubility are our two major physical changes that we need to be familiar with. Does that make sense to everyone? Perfect. So let's talk now about physical properties. So physical properties. Physical properties are any property that are exhibited by a substance without changing its chemical composition or chemical formula. So let's pretend that we have a nice cube of copper, for example. What can we measure about that cube of copper? What can we observe? What data can we collect for this cube of copper without changing its chemical formula? I see someone typing in the chat, volume, that's good, yeah. Yes, we can weigh it, we can record the mass, can also get the density, yeah. What else can we observe about it? Let's pretend we're looking also at a cube of water, an ice cube. We can observe the color. Yep, exactly right. And if we're looking at an ice cube, and we pick it up with our hands, what else can we observe about this copper block and this ice cube? Temperature, yep. And if I'm looking at this ice cube, which is H2O solid, can I figure out what temperature this ice cube melts? Can I figure out the temperature that this ice cube melts? Yeah, it's 0 degrees Celsius, so we can measure the melting point or boiling point. And to help prompt another discussion, if we also are looking at, for example, a cube of sugar, can I figure out how much sugar I can dissolve in water? Can I figure out solubility? Yeah. So solubility would be another physical property to know. So these are some major physical properties. It's not all of them. There are a few that we'll see later on in the class, but these are some major physical properties that are commonly reported and that we'll actually be measuring this week in laboratory for different compounds. Does this make sense for physical properties? Is everyone comfortable with this idea? So, why does this matter? What's the point behind this? Well, mixtures are commonly separated by physical changes, and separations use physical properties of a substance to differentiate and separate substances without changing the chemical identity. Now you may say this sounds pretty esoteric. Well, we've done this in our day-to-day lives multiple times. So if you've ever sort of brewed coffee in the morning, if you've ever made coffee in the morning, you certainly don't want to drink the ground up coffee, right? So inside your coffee machine, you separate the liquid and the coffee grinds using a filter. So filtration separates substances based on their solubility. So the coffee grinds are not soluble in water. They're stuck on the filter. The coffee, the liquid water that contains dissolved substances, passes through the filter and you collect your coffee, which you then drink. Distillation is a technique that separates compounds based on boiling point. So we heat the mixture, the most volatile compound, the compound with the lowest boiling point, then converts from the liquid to the gas phase, the sample boils, and then we can collect the sample as it undergoes a transition back from the gas to the liquid phase. This is a common method of preparing concentrated alcohol, such as whiskey or vodka, where you're distilling off a mixture and you're collecting the relatively pure alcohol via distillation. And again, this is a separation based on boiling point, while filtration is a separation based on solubility. So we use these separation techniques, we use physical properties in our day-to-day lives. Essentially, yes. Well, depending on the type of distillation, the more distillations you perform, the greater the purity, and that's what they call proof. Proof is a measure of purity, and we'll talk about percent purity in our discussion of mass percent, which will be a few chapters later on. So this is just a fun little discussion, as we'll actually be using many of these techniques in the laboratory this semester. So let's take a look at a few examples and we'll classify the following changes as physical or chemical changes. And I'll start off with the first few. So burning methane, so burning. So is this a sign of a physical change or a chemical reaction? If we burn something, if we light it on fire, we react it with oxygen. Chemical, yep, for sure. Melting ice, so we're going from solid to liquid. H2O solid to H2O liquid. Melting, that's a sign of a phase change. And as students are noting in the chat, this is 100% a physical change. Filtering a solid precipitate. So filtering, when we talked about filtration, that's a physical change. Yep, exactly right. Next, I'd like you now to take a few minutes, about 3 minutes, and I'd like you to look at the following set of changes and classify the following set of changes as a physical or chemical change. And I'd like you to share your responses in the chat or verbally. Or if you have a question, don't be shy to ask it in the chat. And remember to look for keywords here. Remember to look for keywords such as dissolves, evaporates, react or reactions. And we'll discuss this example in a few minutes, in about 2 to 3 minutes. And remember, chemical reactions generate or yield new chemical products. Key hallmarks of chemical reactions: generation of gas, production of lighter heat, or generation of a solid. And then remember as well that physical changes and physical properties can include solubility or phase changes. These are some major changes that are physical changes. So we'll give her a few more minutes on this example, and then we'll discuss in about another 2 minutes. To answer the question in the chat, yes, cooking eggs would be a chemical change because you're changing the chemical composition and the chemical formula of each of the reactants found in eggs. It's an irreversible, well, it's a functionally irreversible chemical change. And we'll discuss this example in about 1 more minute. So let's discuss. So evaporates, what does that keyword tell us? Evaporates, what does that tell us? Physical, it's a phase change. And these are physical processes. So heating water removed the dissolved carbon dioxide. So dissolves, dissolved. What does that tell us? Dissolved, that tells us solubility. And is solubility a physical or chemical change? Is solubility a physical or chemical change? It's a physical change, yeah. So anytime you see the keyword dissolves or dissolved, that refers to solubility, which we know as a physical property, and changes in solubility are generally physical changes. Does that make sense to everyone? And the way to visualize this, is initially we have carbon dioxide dissolved in water. And then at the end of our change, after heating, we have forced the carbon dioxide out of solution and we have carbon dioxide gas. As we notice, the chemical formula has not changed. Does that make sense? Does that explanation help clear things up? Perfect. Now for our last example, mixing two solutions. Oh, we see the keyword of mixing, but let's keep reading this problem. Yields. So yield is another keyword that you may want to know. This is a key sign that you're dealing with a chemical reaction. And the real nail in the coffin in this example is that we see mixing these solutions yields a white solid precipitate. And since we are generating a solid tells us what? If we're making a new chemical species, what does that tell us? That we're dealing with a chemical change. So this would be a chemical change. Do these examples make sense to everyone? Does this make sense? Are there any questions that I can address? Someone had a question, boiling water. So boiling water, just as a bonus example. So boiling, we're going from H2O liquid to H2O gas. Does the chemical formula change? Yep. And since the chemical formula stays the same, this would be a physical change. Yep. Phase changes are physical changes. Did that address your question? Not the equation stays the same, but the formula stays the same.
Professor, I have questions.
Yes.
Sometimes we don't know how to write the formula. Then how do we tell that's like a physical or chemical?
Then you'd have to rely on the keywords. So in this case, boiling tells us that we're dealing with a phase change. Thus, because it's a phase change, it's a physical change. Does that make sense? Perfect. In general, if you're not dealing with a phase change or solubility, the change is likely going to be a chemical change. Most of the changes that we'll see in the laboratory and in day-to-day lives where we're dealing with chemistry are often going to be chemical changes. So let's keep going, and we're going to classify the following properties or statements as physical or chemical properties. So I'll start us off. Density. And the key thing that you think about for physical or chemical properties, the key thing that you want to think is, can I measure this property without changing the chemical identity of my material? So density, I can take an object, I can weigh it, I can measure its volume without changing its chemical identity. Density is a hallmark and a very clear physical property. The next statement, alkali earth metals react. So I see the keyword react. They react violently with water. So this keyword react tells us we're dealing with a chemical change. The last one, hydrochloric acid is corrosive to the skin and metals. So corrosive. So we may not know what that word means, but we see that hydrochloric acid seems to be interacting with the skin and many metals, and corrosive is a sign of a reaction. So this would be a clear chemical change. Just to help everyone see the difference between and why corrosive indicates a reaction, if we have the statement sugar dissolves in water, dissolves is different than corrosive. Dissolves indicates what kind of property? Physical, yeah. Dissolves concerns solubility, corrosion concerns reactivity. Does that make sense? Perfect. So let's look at the following examples, and I'd like you to classify the following statements as physical or chemical properties. As physical or chemical properties. And we'll take about 2 minutes on this example. And don't be shy to share your responses in the chat or to ask your questions verbally. And if there are any questions I can address in the chat, do not be shy to ask, and I'll be happy to address them. I see in the chat we have a question, and we'll add this one to the list. So a log burns in a fire. We'll talk about this one, but burns, so burns is a key sign of combustion. The log is undergoing a reaction with oxygen. So when a log reacts, that would be a chemical change or a chemical property. So we'll give everyone about another minute on this example, and then we'll discuss these two. There seems to be pretty good agreement, but let's try to get a few more responses in the chat. Really don't be shy to share, because even if your response differs from your classmates, it may not be wrong, one, and it can provide me some insight into how the class is approaching these problems and allows me to develop examples to help clarify. So let's discuss. Sodium chloride dissolves in water. Dissolves, that tells us we're dealing with solubility. And is that a physical or chemical property? As I see overwhelmingly in the chat, it's a physical property. Alkaline earth metals react with water. So we see the key word react. Is that a physical or chemical signpost? Are we dealing with a physical or chemical property? Chemical, react, chemical reactions. And then the last one of your classmates asked, if we see the statement, a log burns in the fire. Okay, burns, combustion, reacts with oxygen, clear chemical change. Do these examples make sense? Okay, so let's talk now about the fundamental particles that make up an atom. So if we have an atom, this is our atom. Atoms are comprised of three fundamental particles: a positively charged proton, a neutral neutron, and a negatively charged electron. So, what do I need you to know from this? What do I need you to know about these protons, neutrons, and electrons? Neutrons are neutral. They have a charge of 0. Protons have a charge of +1. Electrons have a charge of -1. Now, I've made these pictures to help everyone realize this second point. I'd like you to tell me which of these subatomic particles has the smallest mass. Which of these subatomic particles from these pictures, which of these particles has the smallest mass? Which picture is the smallest here? The electron. I'd like you just to know that electrons are very small and are smaller in mass than protons and neutrons. Okay, so in terms of symbols, an electron is written as E-. A proton can be written as H+ or P P+. A neutron is written as N0. So these are ways of representing and describing protons, neutrons, and electrons. Again, electrons have a charge of -1, protons have a charge of +1, neutrons have no charge. So that's what I want you to take away from this discussion. Atoms are made up of smaller subatomic particles. And what we're going to focus on in these next few slides is this idea of, well, how do these subatomic particles behave? How are they arranged? And how do these subatomic particles impact reactivity and properties? Okay. So we have developed as chemists a method of noting the number of subatomic particles found in a given atom. So we call this atomic notation or isotope notation. And there are a few really important numbers that are presented in isotope notation. The first number in the upper left-hand corner is known as the mass number. The mass number represents the number of protons plus the number of neutrons. And we'll see this again below. The number in the bottom left-hand corner, is known as our atomic number. This represents the number of protons. The number in the upper right-hand corner is the charge, and the charge represents the number of protons minus the number of electrons. And the last symbol that we need to be familiar with is that in the center of isotope notation, we have our atomic symbol. And from the atomic symbol, you'll be able to look up this element in the periodic table. Now, there are a few things that we need to look at, and there are a few specific definitions that we need to cover. An anion, as we discussed previously, has a negative charge. So as we can see, this oxygen isotope has a negative charge, so it would be an anionic species. Now, in some cases for isotope notation, you're only given the mass number and the element symbol. But don't worry, there's a trick. There's a trick. Because from the element symbol allows you to find the atomic number in the periodic table. So we have a method to look up our atomic number from the element symbol. Finally, looking at this iron 3+, it's a cation. And cations, as we've discussed previously, have a positive charge. Okay, so these are each of the pieces of isotope notation. Let's now drill down and focus on each aspect of isotope notation individually. Let's focus on each of the pieces one by one. So let's start with the easiest one, the atomic number. So the atomic number indicates the number of protons that our atom has. Atomic number is unique for each element, and it's unique for each element symbol as well. It's a little redundant, but in isotope notation, it's easier just to look at the element symbol to identify the element. So, for example, if we're given the symbol for chlorine, so we're given the following element symbol, we can actually look up from the symbol the atomic number. So we have our symbol, we go to the periodic table, and we see the following little section of our periodic table. So we have our symbol, and then the number above the symbol in the periodic table is known as the atomic number. And this atomic number is equal to the number of protons in our sample. So would someone like to tell me in the chat, what is chlorine's atomic number? 17, exactly right. So then we conclude that chlorine has 17 protons, or 17P+. Does that make sense to everyone? You can look up the atomic number from the periodic table if you know the atomic symbol. So let's look at the next term, which is the mass number. So the mass number represents the number of protons plus the number of neutrons. Now we can rearrange this. Because we want to often in isotope notation count the number of subatomic particles. So we can also rearrange this equation and solve for our number of neutrons. And that gives us the number of neutrons is equal to the mass number minus the number of protons. So let's show how we can use this. Let's suppose for a moment that we have 8 protons and 10 neutrons. Can we figure out the mass number? Can we figure out the mass number from this information? Yeah. So from this information, our mass number would be equal to 8 protons plus our 10 neutrons, which would give us a mass number of 18. Likewise, if we are given in the problem as a separate example, if we're given that the mass number is equal to 24, and we're also given that our number of protons is equal to 12, can we figure out the number of neutrons? 12, yeah. So our number of neutrons equal to 24 minus 12, which would give us 12. Okay, now what's really important to note is the atomic number is the number on top. This bottom number here has a special name. This is known as the average atomic mass. You do not use the average atomic mass for isotope notation calculations. Average atomic mass is used for an entirely different purpose. Does that make sense? Perfect. So the charge is formally defined as the number of protons minus the number of electrons, which are negatively charged particles. So we can also rearrange this equation to solve for the number of electrons. And the number of electrons is equal to the number of protons minus the charge. This is a very useful equation to be familiar with, as it allows you to very efficiently calculate the number of electrons. So let's look at an example. Let's suppose we're given that the number of electrons is equal to 10, and that the number of protons is equal to 13. Can we figure out the charge? Do we have enough information to figure out the charge? Yes. So for our charge would be equal to our number of protons, which is 13, minus the number of electrons, which is 10, and that would give us a charge, and this is what you need to be careful for, a charge of positive 3. Likewise, let's suppose in a separate example, we are given that our charge is equal to -2, and we're also given that our number of protons is equal to 16. Can we figure out the number of electrons? Yeah, so to figure out the number of electrons, we take the number of protons, which is 16, minus the charge, which is -2, which gives us a total of 18 electrons. Does this initial overview make sense? Does everyone see how to perform each of these calculations and use these equations? We'll be doing a lot of practice for these examples. I just want to make sure everyone's comfortable with this so far. Any questions so far? So the charge depends on the number of protons and electrons. In the periodic table showcases neutral elements. And depending on whether we have a cation or anion, where we have excess electrons or less electrons than usual, the charge will vary. Elements prefer to adopt certain charges, as we'll see in later chapters, but each element doesn't necessarily have a set charge. So just as a review to flesh out our definition of anion, anion in this case refers to a negatively charged atom. And more specifically, it is an atom where we have more electrons than protons. A cation is a positively charged atom, which in turn has more protons than electrons. Does this make sense to everyone so far? Perfect. So let's do some examples and let's unpack each of these terms more carefully. So first and foremost, let's look at our and revise our definition of an element. An element is a substance where all atoms of that substance contain an identical number of protons. In other words, where the atoms have the same atomic number. As we've seen previously, each element has a unique symbol with a unique atomic number. You can determine the atomic number from the symbol and the periodic table. So for example, for chlorine, we had atomic number 17. For iron, would someone like to look in their copy of the periodic table and find the atomic number for iron? You're given a periodic table earlier on in these notes. And yes, the atomic number for iron is in fact 26, because the atomic number is the number above the symbol in the periodic table. Okay, perfect. So we can fill in the atomic number. And remember, each unique element has a unique atomic number. Wonderful. Now, in reading the periodic table, once again, when you look at the symbol, the number on top of the symbol is your atomic number. We, of course, have the element symbol below. And then finally, we have the average atomic mass. Now, one thing that I do want everyone to sort of be aware is that we can work in reverse. And if we can go from the number of protons to the atomic symbol. So for example, if we know that our number of protons are equal to 4, which element in the periodic table, has an atomic number of 4? Which element in the periodic table has a 4 above the element symbol? That would be beryllium. So then, from 4 protons, we can assign this element as beryllium. For one more example, if we're given that the number of protons were equal to 10, which element has 10 protons? Which element has an atomic number of 10? That would be neon. So we can work backwards from the atomic number to the symbol using the periodic table. Do these ideas make sense to everyone so far? Does this make sense to everyone so far? Any questions on these examples? Any questions so far? If not, let's keep going now and let's talk about our mass number now. So there's one type, one set of atoms that we need to talk about. They're called isotopes. These are atoms of the same element, same atomic number, with a different mass number and a different number of neutrons. So isotopes, same element, different mass. Isotopes have almost identical chemical properties. They're the same element, but they have different masses. So for example, O18 and O16 would be considered isotopes because we're dealing with the same element. However, they have a different mass number. Now, one thing that students often get tripped up on here is that if I have an element X of the symbol 16/8 and an element X with the symbol 7/18, are these two isotopes? Are these the same element with different masses? No, and we're going to put an X over that. The reason for that is these two compounds, or sorry, these two symbols represent different elements. And as a result, they cannot be isotopes. Isotopes, same element, different mass. Does that make sense to everyone? So, let's keep going now. Isotopes can also be written in shorthand notation where you have the symbol followed by a dash and then the mass number. So oxygen 18 can also be written as O18. Now, what's really useful is that from the atomic number, and from the mass number, we can in turn calculate the number of neutrons. So let's showcase this for oxygen 18. So if we look up the symbol for oxygen in our periodic table, what is the atomic number? What is the atomic number? 8. It's the number above the oxygen symbol. Wonderful. So then, what we can do now is we can calculate the number of neutrons by taking the mass number, which is 18 in this case, minus the number of protons, which would be 8. That gives us a total of 10 neutrons. We can repeat this calculation for oxygen 16. And I'd like everyone just to take a moment and try and tell me how many neutrons does oxygen 16 have to its name? Eight. Perfect. So let's showcase that calculation. So we have 16 for our mass number. We have an atomic number of 8, and that in turn gives us a total of 8 neutrons. Perfect. Perfect. So, any questions on mass number and atomic number?
Professor, can you explain that that example you said, the one where you crossed off with the different elements that it's not
Yes.
isotopes?
So isotopes refer to the same element with a different mass number. And as we notice, for this example, the atomic number is different, right? 8 and 7 are different. And as a result, because they're different elements, these are not isotopes.
Got it. Okay, thank you.
Does that make sense?
Yes.
Perfect, perfect. Any other questions I can address? If not, let's continue on now. So here's your periodic table once again. We can read off our atomic numbers from the periodic table. And we're going to do an example where I start us off, and then you will do a subsequent example. So we're asked to calculate the number of protons and neutrons in the following atom. So bromine 79. So my first order of business is to find bromine's atomic number. So I found bromine and the atomic number is above my element symbol. So I'm going to fill that in. So I know that my number of protons is equal to 35. That's easy. Okay, now for my number of neutrons, we're going to have to work a little bit harder on this one. We're going to take our mass number minus our number of protons. In turn, that gives us, for our number of neutrons, we have a mass number of 79, and we're going to subtract 35, and that in turn gives us 44 neutrons. So our number of neutrons are equal to 44. Does that make sense to everyone? Does this first example make sense? Any questions? So looking at magnesium 24, what is this 24 representing? What is this 24 representing?
Neutron.
You're on the right track. The 24 is representing our mass number. So when you see magnesium 24, think of it like this, where our mass number is 24. That's critical because it allows us to now calculate the number of neutrons. So before we do that, first we need to look at magnesium and we need to find the atomic number. So for magnesium, our atomic number is 12. So now that we have the mass number, which is different than atomic mass, this is the mass of this specific, this is the total number of protons and neutrons for this specific atom. What we're going to do now is we're going to calculate the number of neutrons. And to calculate the number of neutrons, we're going to take our mass number of 24 minus the number of protons, which is 12, and that gives us 12 neutrons. From the atomic number, we know that our number of protons is equal to 12. Does this example make sense to everyone? So in this form of isotope notation, the number after the dash is the mass number, which is the total number of protons and neutrons. And we use the mass number to in turn calculate the number of neutrons.
Professor, where do we see the number 24 on the magnesium? On the chart?
This isn't on the periodic table. Just like an isotope symbol that I would give you, you would be given this entire symbol on a test or quiz.
So we would just look under magnesium?
Yes. So this 24 is given. This is referring to this specific isotope. And this number is the mass number for this specific isotope, for this specific atom of magnesium. Does that make sense?
Okay, yes. That one will always be given to us then.
Yes, yes. I could just as easily have given you magnesium 25 or whatever number I want.
Okay.
you're asked just to calculate the number of protons and neutrons for this specific isotope. The numbers that you see below the element symbol, don't worry about them just yet. Those are representing the average atomic mass, which is used for an entirely different set of calculations. Does that make sense?
Yes, thank you.
Perfect. So now that we've seen a representative example, here's a periodic table, and I'd like you now to calculate the number of protons and neutrons in the following atoms. And you may see some weird ones on this list just to make it harder to Google. So you just have to be familiar with your calculations, since some of these isotopes aren't very common at all. So I'd like you to calculate the number of protons and neutrons in the following atoms, and then we'll discuss this example in about 3 to 4 minutes. And let's try to get a few more responses in the chat. And if you're unable, if you don't want to provide a response, you can also ask a question in the chat or ask a question verbally, and I'd be happy to clarify whatever questions you have. We'll discuss this example in about another 3 minutes. And let's try to get a few more responses in the chat, and we'll discuss in about another 2 minutes. And the responses I'm seeing in the chat look good so far. Let's try to get a few more responses before we discuss in about another 1.5 to 1 minute. And if there are any questions I can address, don't be shy to ask. Otherwise, let's get started for this example. So for neon, looking up neon in the periodic table, we see we have an atomic number of 10. Okay, so that's an easy one. We can figure out our number of protons equal to 10, which matches our atomic number. Our number of neutrons, however, we calculate that by taking the mass number minus the number of protons, or 20 minus 10, to give us a total of 10 neutrons. Does this example make sense to everyone? Does this make sense? Any questions on this first example? If not, let's look at magnesium. So when you say so the neon represented in the periodic table is the average of all, it represents the average mass of all the isotopes weighted by abundance. So when you say regular neon, there's no symbol with a mass number for regular neon. Rather, mass number is specific to a given isotope or atom of neon. Does that make sense?
Kind of. Just isn't it the same number of protons and neutrons then when it's the average amount of like the mass number?
So it's not entirely correct to say that, just because the element symbols and the masses represented in the periodic table are the average of all the isotopes that are weighted by abundance.
Uh-huh.
So if we looked at if you were to view an average atom of neon, it wouldn't really be appropriate to write a mass number. What we can say in general is that the majority of our neon atoms are neon 20. And that would be so most of the atoms of neon in nature are going to be neon 20 or some variant of that.
Okay.
It just has to do with the fact that in nature, there are different amounts of each isotope, and the periodic table averages the abundance and mass of these isotopes together when reporting the average atomic mass. Does that answer your question?
Mm-hmm.
Perfect. So for magnesium 13, so we've already seen that we know magnesium's atomic number is 12, so we know our number of protons is equal to 12. Just to remind everyone of where we got that. So if we look up magnesium, we see our atomic number of 12. So then, the number 13 indicates our mass number. Ergo, we know our number of neutrons is in turn equal to our mass number, which is 13, minus the number of protons, which is 12, which gives us 1 neutron for the following isotope. Does this make sense to everyone so far? Any questions on this example?
So just to recap, protons are equal to the atomic number, correct?
Yes. Mm-hmm.
And then in order to find the neutrons, we subtract the mass number from proton?
Could you repeat that one more time?
Yeah. So in order to find the number of neutrons, do we do the mass number minus the proton? Is that?
Yes, that's exactly right. So
Okay.
the number of neutrons is equal to the mass number minus the number of protons. That's exactly right. So in this case, to calculate the number of neutrons, we take our mass number of 13 minus the number of protons, which is 12, which gives us 1 neutron. Does that make sense?
Yes, thank you.
Perfect. Are there any other questions I can address? If not, let's keep going. And let's talk about ions now, which will prompt our discussion of the other subatomic particle on our list, which is the electron. So ions are the same element, same atomic number, same number of protons, but they have a different charge. So for example, as we can see here, we have a charge of 0 for the following oxygen atom. Note, we don't typically write the charge of 0, we just leave it as a blank space if the species has a charge of 0. Compared to, in this case, we have a charge of -2, where we have an anion. Now, ions, we have the same element, but as we can clearly see, our charge is different. So we have a different charge. In general, an ion is a general phrase for any charged atom. In this specific case, we use the description ion to refer to two atoms of the same element with a different charge. Now, from the atomic number or the atomic symbol, we can calculate the number of electrons if we know the charge. So, there are two different types of species for ions. An anion, which is a negatively charged ion. I like to write a minus just to remind myself of that. So looking at, for example, sulfur 32 2-, we know the charge is equal to the number of protons minus the number of electrons. So we need to go to the periodic table now. And what is the atomic number for sulfur? How many protons does sulfur have to its name? $16, yep. Okay, perfect. So we know that our number of protons is equal to 16. Okay. So rearranging this equation, we can solve for the number of electrons. And the number of electrons is equal to the number of protons minus the charge. Okay, so plugging in our numbers here, our number of electrons is equal to 16 minus our charge, which is -2. And that in turn gives us a total number of electrons of 18. Does this make sense to everyone? Let's look at a cationic species such as potassium. So a cation is a positively charged ion, positive charge. And just like before, we can figure out the number of electrons by taking the number of protons minus the charge. So then, for potassium, we need to figure out the number of protons by looking at the atomic number. So how many protons does potassium have to its name? Potassium has an atomic number of 19, so in turn, it has 19 protons. So then, solving for our number of electrons, we get 19 protons minus the charge of +1, that gives us 18 electrons. Now, there's a special word that we use to describe species or ions with the same number of electrons. So isoelectronic is used to refer to two atoms or ions with the same number of electrons. So we could say, for example, S2 minus and K plus are isoelectronic because both of these ions have 18 electrons total. Does that make sense to everyone? Any questions before we move on to the next idea?
Does that say at the end two atoms or ions with the same number of electrons over number of electrons?
Not divided. I just was showing the symbol as number of E minus. So it's not an not an equation, but I'll just
Gotcha,
try
thank
to just try to space it out like that, just to. Does that make sense?
Yes.
Perfect. Any other questions before we move on? Okay, so let's look at an example where we calculate the number of protons and electrons in the following ions. I'll start us off for this one and then you'll do the next one. So we're looking at N3 minus. So nitrogen in the periodic table has an atomic number of 7. So we know our number of protons is equal to 7. So then if I wanted to calculate the number of electrons, all we do is take the number of protons minus the charge. So then the number of electrons is equal to 7 minus our charge, which in this case is -3. And that gives us a total of 10 electrons. Aluminum 3 plus. Aluminum, if we look at the periodic table, aluminum in the periodic table has an atomic number of 13. Ergo, our number of protons is equal to 13. In turn, we can calculate our number of electrons, which is equal to our number of protons, which is 13, minus the charge, which is +3. So aluminum 3 plus has a total of 10 electrons. Do these examples make sense to everyone so far? Does this make sense to everyone so far? Okay, so let's now try and let's have you work on the following 2 examples and calculate the number of protons and electrons in the following ions. And we'll discuss this example in about 4 minutes. So let's work through this problem and then we'll discuss in about 4 minutes. And don't be shy to submit your responses in the chat for the number of protons and electrons for the following ions, and we'll discuss in about 3 to 4 minutes. And it's good to see a reasonable pool of responses in the chat. Let's give everyone a few more minutes, and don't be shy to submit your response, even if it's different than your classmates. The more responses that we see, the better I'm able to provide feedback and provide additional examples.
Professor,
Yes.
so no matter how many charges they are, the protons and the neutrons will never change, right?
For the number of protons for the same symbol will be the same. So for example, chlorine always has the same number of protons. The number of neutrons, it depends on the mass number. Does that make sense? Perfect. Let's try to get a few more responses and we'll discuss in about another minute. So let's discuss this example. So looking at Cl minus or chloride. So for chlorine, if we look in the periodic table, what is chlorine's atomic number? What is the number above chlorine's atomic symbol? Would anyone like to provide a response? How many?
17.
17, yep. So then the number of protons for chlorine is 17, okay. So then we know that the number of electrons is equal to the number of protons minus the charge. So then the number of electrons is equal to 17 minus -1. That gives us 18 electrons. Does this first example make sense? Okay, let's look at calcium, and we're going to repeat the exact same pattern here. So calcium has what atomic number? What is the atomic number of calcium?
20.
20, yep. So then the number of protons in turn is going to be equal to 20. And in turn, that means, so our number of electrons is equal to the number of protons, which is 20, minus the charge, which is +2. So for our number of electrons, we have 18 electrons. Now, from these examples, does anyone notice a trend and something that seems a little strange for the number of electrons for all of these ions? How many electrons are we often seeing for our ions? What number of electrons comes up pretty frequently for a lot of our ions? 18, 10. So you may just want to take a note on this 18 electron idea. 2, 10, 18. We're going to come back to this later on. The number of electrons for ions will usually fall in this pattern. And what we're going to talk about later on in this chapter are trends in ionization and why different ions prefer to have a certain number of electrons. So this is just a teaser for later on in the class. This 18 electron trend that we're seeing is not just random coincidence. It's based on periodic trends of stability. We'll talk about that later. So let's do a higher order example. And in this case, we're asked to list the number of protons, neutrons, and electrons in each of the following ions. So this is really putting everything together here. So what I'm going to do is I'll start off with these first two examples, and then you'll do the next set. So just to see, we have another set of examples later on for this topic. So dissecting this isotope symbol in detail, I was nice and I gave us the atomic number already. So we know our number of protons is equal to 35. We know as well that our mass number is equal to 81. And we also know that our charge is equal to -1. So from this information, we can calculate the number of neutrons by taking the mass number, which is 81, minus the number of protons, which is 35. That gives us 46 neutrons. And then if we want to calculate the number of electrons, we take our number of protons, which is 35, minus the charge, and that gives us 36 electrons. Does this example make sense? Does this first example make sense? It's just putting together all the parts that we learned in the earlier part of this section. Does this make sense to everyone? Any questions?
I have a question. So whenever there's just a negative and no number on there, it's just automatically a -1?
Yes. So in general, we don't write the number 1 or 0 in isotope notation to avoid redundancy. Yes. So if you just see a negative sign, that's implying a charge of -1.
Got it. Thank you.
Mm-hmm. So let's look at this example where we have iron 56, 3+. If we look at iron in the periodic table, as we've seen in earlier examples, iron has an atomic number of 26. So then our number of protons are equal to 26. We also know, again, just writing out the information that we know, the mass number is 56. And the charge is equal to -1. So then, looking at the number of neutrons, we take our mass number, which is 56, minus our number of protons, which gives us 30 neutrons. Next, we calculate the number of electrons.
Professor, wouldn't it be 3? Why is it -1 charge?
Oh, sorry about that. The charge in this case would be +3. Sorry about that. I'm not sure what happened there. Let me readjust that calculation. So for our number of electrons, we take our number of protons, which is 26, minus the charge, which is +3, and that gives us a total of 23 electrons. Sorry about that. There we go. And the charge is found up here in the upper right-hand corner. So just to recap, our atomic number, which is the number of protons, is 26. The mass number, which is found in the upper left-hand corner, is 56. The charge is +3. Our neutrons are equal to the mass number minus the number of protons, giving us 30 neutrons. And our number of electrons is equal to the number of protons minus the charge, which gives us 23 electrons. Does this example make sense to everyone? So let's look at another example where we're asked to write the isotope symbol for an element with 26 protons, 30 neutrons, and 24 electrons. So in this case, we're working backwards here. So let's summarize what we know. So we know our number of protons is equal to 26. Our number of neutrons is equal to 30. And we know our number of electrons is equal to 24. Okay, so in writing the symbol, first things first, let's figure out what element we're dealing with. So what element has an atomic number of 26? Iron. Okay, so we write our symbol, and then we can also write our atomic number, though that is slightly redundant. Now, our mass number is equal to the number of protons plus the number of neutrons, which in turn gives us 30 plus 26. That gives us a mass number of 56. And then our charge is equal to our number of protons minus the number of electrons, which is equal to 26 minus 24, which gives us a charge of +2. So this would be the symbol for an element with 26 protons, 30 neutrons, and 24 electrons. Is everyone comfortable with this idea, working backwards here? Is everyone comfortable with that? Okay. Any questions before you work on the next set of examples? Okay, so let's work on the following example. Let's indicate the number of protons, neutrons, and electrons in phosphorus 31 3- and barium 138 2+. So this will be the last example set for today, and we'll discuss this example in about 4 minutes. And let's try to get a few more responses in the chat, and we'll discuss in about another 2 to 3 minutes. And it's good that we have a reasonable pool of responses in the chat, and we'll discuss in about another minute to a minute and a half. And if you have any questions, don't be shy to ask. Okay, so let's discuss these examples. So first we have phosphorus 31, 3 minus. So for phosphorus, what is the atomic number in the periodic table? Let's get some responses in the chat for that. 15. Okay, perfect. So we know that our number of protons is equal to 15. Okay, let's now calculate. We know as well that our mass number is 31. And we know that our charge is equal to -3. So then we can solve for the number of neutrons by taking our mass number minus the number of protons, which gives us 16 neutrons. And we can solve for our number of electrons by taking our number of protons minus the charge. That gives us 18 electrons. Does this first example make sense to everyone? Does this first example make sense? Okay, let's work on the next example. So for barium 138 2+, what is the atomic number of barium? What number do we see in the periodic table above barium? 56, okay. So now what we're going to do, we know that our number of protons is equal to 56. We also know that our mass number is equal to 138. And we know our charge is equal to +2. So then that in turn gives us our number of neutrons is equal to 138 minus 56, which gives us 82. And our number of electrons is equal to our number of protons minus the charge, which gives us 54 electrons. Does this example make sense to everyone? Any questions on this example? Okay, so this will be the end of today's lecture.